This video indicates two main uses of SU Near Surface Zone CSV and SUMATRIX. The first main use is to check the trace header geometry values. The second main use is to confirm that a simple near surface model fits the refraction wavelet times in the trace seismic data. This video then goes into a lot of details related to statics, approximations, and miscellaneous options and uses.
If you are unfamiliar with simple near-surface layers, see my video, Manually Deriving Refraction Statics for Simple Near Surface. Also, basic tests for SU Near Surface Zone CSV and SUMATRIX exist in the demos directories. Contents of this video. 1. Geometry checking concept using simple 2D example. 2. Simple 3-layer example. 3. Using a spatially varying refraction model. Input a Q file. 4. Spreadsheet computation of refraction model statics. 4a. Improving the refraction model top layer. 5. Refraction model and travel path approximations. 6. Miscellaneous options and uses. 1. Geometry checking concept using simple 2D example. Consider the traces of a simple 2D survey split spread shot. The shots in this survey typically have 30 traces on one side of the shot, a 1 trace gap at the shot location, and 30 traces on the other side of the shot. For a simple near surface, the refracted arrivals look something like this image. For that simple case, this zero offset intercept time is approximately proportional to twice the top layer thickness divided by the top layer velocity. And the slope of the refracted arrivals here is the velocity of the next layer. That is, for a shot on the surface, the refracted arrival path is downward through the top layer, along the top of the next layer, and then upward through the top layer. Specifying a simple setup of SU Near Surface Zone CSV will flatten the refracted arrivals. In this case, the top layer is 15 meters thick with a velocity of 610 meters per second. The next layer has a velocity of 1200 meters per second. The resulting output traces look something like this. By default, SU Near Surface Zone CSV adds an extra 200 milliseconds to output. If you specify a second layer velocity of 1300 instead of 1200, the output looks like this. If you specify a second layer velocity of 1100 instead of 1200, the output looks like this. Also, of course, if you alter your specified top layer thickness or velocity, all traces will be shifted up or down in time. So, with reasonable values, the output shots all look something like this. But what if the traces of a shot look like this? Well, this almost always indicates some kind of geometry error. By geometry error, I mean that the input trace headers have some wrong values. You can, of course, examine every shot gathered individually after SU Near Surface Zone CSV, but some geometry errors are not as obvious as was just displayed. The SUMATRIX program makes it easier to see these errors. On initial viewing, the output of SUMATRIX may appear confusing. So I am starting here with a close-up display of the SUMATRIX output traces. There are 3 shots here. Each output trace has the same receiver number. The neighboring shots show the geometry error of the middle shot quite clearly. Zooming out a bit, the output of SUMATRIX looks like this. By default, SUMATRIX assembles its output traces in groups of 20 shots. Note that you can still see the geometry error. Zooming out to see all traces output by SUMATRIX looks like this. You can see that the shots are assembled in groups of 20. Note that each trace is assembled from the refraction wavelets of one receiver, but that same receiver often exists in more than one set of 20 shots. Looking carefully, you can still see some geometry errors. Investigating the first geometry error, one possibility is that the trace headers have the wrong shot trace header values. This could produce the wrong shot to receiver distances for all traces of that shot. So, first look at the shot XY coordinates, shot elevation and shot depth. Those values are in the input trace headers, but usually originate from some file. The file shown here is an SPS2S file. If you are unfamiliar with SPS2 files, see my videos about geometry update. However, it is actually more likely the error is in the SPS2X file. The SPS2X file contains the shot point number to assign to a field record number. The traces with that shot point number are then updated with the values of that shot from the SPS2S file. So, having the wrong shot point number here will result in the traces getting the wrong shot coordinates, shot elevation, and shot depth. Even without specifically using SPS2 files, similar errors can occur. Observer notes can also easily indicate the wrong shot point number. Finding that it was a shot point number error, correcting it, and re-updating the geometry in the trace headers, this is the result. Before continuing, I want to point out these traces. Note that the refraction wavelets assembled in each of these SUMATRIX traces have the same small time shift relative to their neighboring receivers. Remember that each trace here is assembled from one receiver. So, if the receiver is near a rapid change in elevation, or is noisy, or is dead, or is reversed, there will usually be some consistent effect like this. Looking now at the second geometry error, it looks very similar to the first error, but it is not a shot error. Instead, every trace header for the middle shot has the wrong receiver coordinates and elevations. But all shots near this one have the same receiver coordinates, and they are good. So how could only the traces of this one shot have incorrect receiver coordinates? Well, again, that could occur due to an error in the SPS2X file. The SPS2X file contains the trace number range and receiver number range, which are used to compute the receiver number for each trace number in a shot. The receiver range is often set automatically from one shot to the next. You may have heard of the roll-along switch. In any case, if an unusual shot is taken, it is easy to forget to readjust the range, which will result in every trace header of that shot having the wrong receiver number and therefore also getting updated with the wrong receiver coordinates and elevations. So, how can you tell the difference between these two types of geometry errors? Well, note again that some refraction wavelets have a small time shift. But the small time shifts are not on the corresponding wavelets in the middle shot. Instead, they are over here. After finding the receiver range error on the X file, correcting it, and re-updating the geometry into the trace headers, this is the result. The small time shifts all line up. Note that the corrected middle shot is still different than its neighbors. But that is all right because shots do not have to look the same. Here, for instance, shots at the beginning of a 2D survey are rolling into the spread. So the set of receivers is the same in the early shots. Sometimes shots can have odd layout spreads due to obstructions or other reasons. Often this occurs for makeup shots and so on. Section 2, simple 3-layer example. For a 3-layer situation, you may initially think of an image like this, but this is more like a diagram of first break pick times. A 3-layer situation is more like this. Actual wavelets continue to exist even when they are not the first arrival. In fact, a 3-layer situation is even more like this. Both refraction wavelets continue to exist, and so does the direct arrival wavelet. First break times are, of course, the minimum arrival time of all these wavelets. Except, of course, near the shot. Reflections from the near-surface layers arrive before the refraction wavelets. SU near-surface zone CSV does not compute reflection times. SU near-surface zone CSV computes direct arrival time and arrival times for all refraction layers. By default, it applies the minimum of all these times, as shown in the image above. But the t-path parameter allows you to select which of these times to apply. Thus, you can apply the computed direct arrival time, t-path equals 1. So the direct arrival wavelet should be flat, as shown above after SU matrix. Note, SU near-surface zone CSV includes shot depth in direct arrival distance. See section 5. Or you can apply the computed first refraction time, t-path equals 2. So the first refraction wavelet should be flat, as shown above after SU matrix. Or you can apply the computed second refraction time, t-path equals 3. So the second refraction wavelet should be flat, as shown above after SU matrix. And consider another situation. Here, the second refraction wavelet never becomes the first arrival. But you can still apply the computed second refraction time, t-path equals 3, as shown above after SU matrix. This allows you to produce and check a refraction model that has more layers than can be derived from first break picks. Section 3. Using a spatially varying refraction model. Input a Q file. To this point, the refraction model was input via thick-add and val-add, as above. But a spatially varying refraction model can be input via Q file, as below. But where does a spatially varying refraction model Q file come from in the first place? One way is outlined in my videos, Spreadsheet Statics and Manually Deriving Refraction Statics for Simple Near Surface. But you can also start by using SU Near Surface Zone CSV itself without a Q file input. Simply try different thick-add and val-add values at different shots along the survey, and manually record the values which correct the wavelets the best at those shots. If you have SPS2 S files or R files, you can then proceed as in Spreadsheet Statics. Or you can use SU StackUp to make a shot stack or a receiver stack. And then use SU GetQCSV to produce Q files from the headers of those stacks. SU StackUp preserves good shot key values or good receiver key values. And then update that Q file with your manually recorded thick-add and val-add values. An input Q file will look similar to this. Note that this Q file only has values every 40th station. Since the values only exist every 40th station, option LOX equals 1 is recommended in the setup of SU Near Surface Zone CSV. The locus equals 1 option means the model values nearest the trace header shot coordinates are used for both the shot end and the receiver end time computations. Otherwise, the receiver end times would undergo a discontinuous jump when the trace receivers switch from being nearest one Q file record to being nearest another Q file record. This is also explained in section 5. The names used for coordinates, thicknesses, and velocities in this file correspond to the spreadsheet used in my video about manually deriving refraction statics. The above setup shows a 4-layer specification. Any number of layers can exist in the Q file, but thicks and vels parameters default to 3 layers, 2 thicknesses, and 3 velocities. To use different names in the Q file or more than 3 layers, you have to specify the names as shown above. The Q file for the previous setup. Note the extra names and extra values in records. Names values in Q files do not have to be in any particular order, and they can be intermixed with names values that are not being used by SU near surface zone CSV. The above setup shows the use of thick add and val add parameters with a Q file. These values are added to all the values from the Q file before times are computed. This allows easier testing of how well the model fits the traces at different locations. Eventually, you have to manually edit the Q file to change the model. Note once again the use of locus equals 1 in the above setup. You generally want to perform this kind of testing when the Q file contains widely separated locations. Explained later in section 5. Looking again at the Q file, which only has values every 40th station, after manually updating model values, this Q file can be interpolated and smoothed, and then statics can be computed. See section 4. Here are setups of SU bin Q CSV and SU SMOC CSV, which linearly interpolate and smooth the previous Q file values. See my videos about those programs. You can use either of these 2 new Q files in SU near surface zone CSV. Note that locus equals 0 is now specified in the SU near surface zone CSV setup because this refraction model has values at every station. See section 5. The interpolated and smoothed Q file looks like this. This file has values every station. Section 4. Spreadsheet computation of refraction model statics. Previously, at the end of section 3, we obtained an interpolated smooth Q file which contains layer thicknesses and velocities, but it does not contain any statics. It also does not contain any elevations or shot depths, and even if it did, those elevations and shot depths would be interpolated smoothed. Smoothed elevations and depths are usually not good in statics computations. So, to compute statics, we need to merge the original elevations and shot depths with the Q file that came out of SU bin Q CSV and or SU SMOC CSV. To compute statics in this situation, it is easiest to start from my spreadsheet, which already computes statics. You can find a link to the spreadsheet in the description section of my spreadsheet statics video. Also, in Seismic Unix, demos, SU shift CSV / L2R _ spreadsheet _ test.ods. I assume some viewers of this video are not familiar with spreadsheet programs, so I show many small steps. In any case, my knowledge of spreadsheets is limited. There are probably shortcuts that I have missed. The steps in the following procedure are First, download the spreadsheet and change its name. This spreadsheet contains two types of equations. One type uses time offset pairs to compute layer thicknesses and velocities. The other type uses layer thicknesses and velocities to compute statics. We're going to copy layer thicknesses and velocities into this spreadsheet. So we need to delete the equations which compute thicknesses and velocities, but retain the equations that compute statics. To confirm that we accomplished this correctly, first copy row 13 into row 15. Now click on cell O15, which contains the top layer velocity, named VW herein. Note, there is no equation in cell O15, so VW is not being computed by this spreadsheet. Now click on cell T15, which contains the second layer velocity, named VB here. Note, there is an equation in this cell, so VB is being computed. Delete the equation in cell T15 and type in the actual numeric value it had. This is the same number that is in row 13. Remember, we copied row 13 to row 15. Notice that the next two static values, columns X and Y, retain their values. If you change the T15 value, the statics in X15 and Y15 will change as well. This showed that the statics computing equations are still functioning as intended. Now click on cell W15, which contains the top layer thickness, named Z_true here. Note there is an equation in this cell, so ZW_true is being computed. Delete the equation in cell W15 and type in the actual numeric value it had. Again, notice that the next two static values, columns X and Y, retain their values. This shows that the statics equations are still functioning as intended. Also delete the equation and substitute the actual number for cell AE15. Notice that the next two static values, columns AI and AJ, retain their values. This shows that the static equations are still functioning as intended. And delete the equation and substitute the actual number for cell AH15. Notice that the next two static values, columns AI and AJ, retain their values. This shows that the static equations are still functioning as intended. Select and delete rows 7 to 14. The only row remaining contains the cells where equations were deleted, but it still retains cells where statics equations continue to exist. Now, read in the interpolated smooth Q file into another spreadsheet. We need to copy some of those values in columns into the main spreadsheet. We need to copy the columns from CSUID names Grunloff, VW, ZW_true, VB, ZB_true, VC into the columns with the same names in the main spreadsheet. For instance, here are the Grunloff values after copying them. Note that I have copied them below row 7. Row 7 is currently the only row that contains equations to compute statics. Also copy these values into their appropriate columns in the main spreadsheet. Part of which looks like this, and part of which looks like this. Put your datum elevation and replacement velocity into columns D and E. Now put the elevations into column J and the shot depths into column F. You might find this awkward. If you have shots every 2 or 4 stations, then you will only have shot depths every 2 or 4 stations. You'll have to copy them to column F and then manually move them to align with their corresponding station in column C. Or you can use SUToolCSV to convert an SBS2S file to a CSVQ file and then interpolate that file using SUBinQCSV as below. Then copy the shot depths to this spreadsheet. The depths on shot stations will remain the same, and it does not matter what depths are interpolated to non-shot stations. Next, do not forget to set the first column to Q. Now, copy cell X7 to all rows below it. Remember that row 7 contains all the statics equations. The equation from X7 is automatically changed by the spreadsheet when copied. All rows below X7 now have computed statics values. The name GStat layer 1 stands for one layer static value for receiver. Copy cell Y7 to the rest of column Y. This is one layer static value for shot. Copy cell AI7 to the rest of column AI. This is two layer static value for receiver. Copy cell AJ7 to the rest of column AJ. This is two layer static value for shot. Note that the statics naming convention within this spreadsheet is arbitrary. You can name them whatever you want. There are other statics equations in this spreadsheet. You can copy cells K7, L7, M7, N7 to the rest of the columns if you wish. However, note that the column M equation uses a value from column G. Column G contains the shot uphold time. So, if you want column M to contain the correspondingly correct static, you need to supply uphold times in column G, like this. There are also columns for coordinates. You should update them, but they are not involved in statics computations. Delete row 7. Remember, row 7 was only retained because it contained the equations. Output a CSV file. This file has the shot station name Gronloff in cell C6. Change cell C6 to receiver station name, gaps, and output another CSV file. Input both files to SU shift CSV to apply both shot and receiver statics. In a 3D survey, you usually need two identifiers. Here, cell B6 has the receiver line name, and the rest of column B has the line numbers. The SU shift CSV setup for a 3D survey would usually use these two identifiers like this. Section 4A, improving the refraction model top layer. Consider the surface elevations of a 2D survey, like the example below. Often, a spatially varying refraction model has averaged interpolated smooth layer thicknesses and velocities. Since the top layer thickness is smooth, the bottom of the top layer looks like this. This is also the top of the next layer, of course. This is not very realistic, but quite often that does not matter. The usual purpose of the refraction model is to produce good long wavelength statics. Short wavelength residual statics will be resolved afterwards by SU res CSV. But if you want a more realistic top layer, use the spreadsheet and SU SMOC CSV. To do so, first subtract the top layer thickness from the elevation and put that value into a new spreadsheet column. That value is the actual elevation of the bottom. Then output a CSV file and smooth those new values via SU SMOC CSV. That produces the blue line below, which is the smooth elevation of the bottom. Copy the blue line values back into the main spreadsheet. Then reset the top layer thicknesses to the difference between the surface elevations and the blue line values. So now the top layer thicknesses vary rapidly. Now the model looks like this. The spreadsheet will recompute the statics, of course. Using those statics is all right since short wavelength residual statics will be resolved afterwards by SUNSZONECSV anyway. These residuals will have different values for the two models, but the total statics after SUNSZONECSV should be the same. As well as making a more realistic looking model, the preliminary stack will likely be better focused because the bottom of the top layer probably is actually smooth. Next, remember that SU near surface zone CSV has the t-path equal 1 option, which applies the computed direct arrival time. The direct arrival distance is computed from shot's elevation minus depth to the receiver's surface elevation, see section 5. So t-path equals 1 can be used to try various top layer velocities to see which value is best, provided the top layer is thick enough to actually see direct arrivals on the traces. So often you can improve your estimate of the top layer velocity. Extending this topic slightly, the residual statics output by SUNSZONECSV are probably produced by rapid variations within the top layer. Making that assumption, you can alter the top layer to produce changes in the model statics which equal the residuals. The altered thicknesses velocities can be closer to the true values. Trying to incorporate your residuals into the top layer requires interpretation decision. So I'm not supplying equations or further guidance. Even if you do it perfectly, nothing will be gained in terms of statics since the total statics will be the same. I mention it because you might have some other reason to improve the top layer. Section 5, Refraction Model and Travel Path Approximations. For a simple two-layer model and a surface shot, this equation computes top layer thickness from intercept time, top layer velocity, and second layer velocity. If you have estimated the weathering thickness and the weathering velocity and the next velocity, you can, of course, rearrange this equation to derive the intercept time. In general, the n-layer intercept time can be computed as below. You can find this n-layer intercept time equation online. The SU near surface zone CSV program performs this computation. You just need to supply the thickness and velocity values. Now, remember that the intercept time consists of contributions from both the shot end and the receiver end of the travel path. For perfectly flat layers with no changes in thickness or velocities, then the intercept time is half from the shot end and half from the receiver end. As well, to compute the refracted arrival time, the distance from shot to receiver is also used, along with the velocity along the top of the next layer. But elevations and layer thicknesses and velocities usually change. The SU near surface zone CSV program does not try to determine the true path. Instead, for every trace, it makes simplifying assumptions using only the information at the shot end and at the receiver end. Essentially, the layers are treated as flat at both ends, and the path between is treated as straight with a linear change in layer velocities between shot and receiver. In addition, the shot may be in a hole. The SU near surface zone CSV program uses shot depth from each input trace header when it computes the time for the shot end of the path. Using the layer thicknesses and velocities near shot and nearest receiver and the trace header shot depth, SU near surface zone CSV computes the intercept time. Part of the intercept time comes from the shot and part from the receiver. These parts include subtracted horizontal components and are also called delay times. Using coordinates and elevations from the trace headers and layer thicknesses, SU Near Surface Zone CSV computes the travel time along the straight green line above. The velocity along that line is assumed to change linearly between the shot end and the receiver end. Note, SU Near Surface Zone CSV is using an approximation here and here. The end-related computations subtract the horizontal components times using the exact end velocities, but the distance-related computations add the angled components times using linear change in velocity along the components. Now, a three-layer diagram with a shot in the second layer. Note dotted green line directly from the shot's true elevation, which includes depth, to the receiver's true second layer elevation. This dotted green line is used to compute the distance-related time for the second layer. Also note that, along with trace header shot depth, the difference in trace header elevations between shot and receiver is used to compute distance-related times for all layers. So even when the refraction layer thickness and velocities are identical at the shot end and at the receiver end, the distance-related times are not just computed from the trace header XY coordinates. Another shot depth-related detail. If the shot depth is within the first layer, the direct arrival time is computed from the shot's true elevation to the receiver's surface elevation. Yet more shot depth-related details. If a shot depth is within a deeper layer, a similar dotted green line is defined. Travel times for that layer are therefore correct, considering other approximations. But setting t-path to a layer number less than the layer containing the shot depth will generate incorrect times. I deliberately made those incorrect times large so that the t-path equals 0 default should still produce the minimum travel time shift. Here is a top-down view of a simple 2D survey with a small curve in the line. The green lines indicate the travel paths computed by SU Near Surface Zone CSV from a shot to two receivers. The true travel paths would, of course, be some complicated curves from the shot to each receiver. The true travel paths are affected by the thicknesses and velocities in the entire subsurface volume. Now, model values have been determined every 40th station, such as M and N. For option locus equals 0, SU Near Surface Zone CSV uses the model values nearest the trace's shot coordinates for the shot end and the model values nearest the trace's receiver coordinates for the receiver end. Option locus equals 0 is generally a bad idea for widely separated model locations like this. For option locus equals 0, the trace receivers near R will suddenly switch from using the model values at M to using the model values at N. This will result in rapid, discontinuous time shift jumps within the same shot. Option locus equals 1 is generally better for this kind of situation since it uses the model value nearest the shot coordinates for all traces of a shot. Section 6. Miscellaneous options and uses. For 3D surveys, you generally need to identify two trace keys in SUMATRIX to identify the receivers. RKey loc equals GRONORs and gaps, and possibly SKey loc equals GRONOFF and GRONLOFF to identify shots. These key names are what I defaulted in SU Geom CSV for geometry from SPS2 files. But for shots, you still might want to use the FLDR key as shown in the setup above. The field record number, FLDR, is usually in order of shot acquisition. And for 3Ds, you usually should set rfill equals 0, or the output will have many empty traces. Even with rfill equals 0, a 3D survey requires getting used to. This is just the first 20 shots. Here, each shot has 12 traces on 4 receiver lines. There are many receivers that exist but do not appear in the first 20 shots. The rfill equals 0 suppresses empty traces for them. The S divider and R divider parameters in SUMatrix can reverse the order of shots and receivers, which may make easier understanding for some acquisition direction numbering conventions. Setting the SUMatrix parameters S divider and R divider to -1 will reverse the order that shots and/or receivers are assembled. Like this, for example. The S keyloc and R keyloc parameters in SUMatrix do not actually care whether they are shot key names or receiver key names. Using opposite names will exchange the axes. For instance, sets of 20 receivers can be assembled instead of sets of 20 shots. Each set of 20 receivers will contain one trace from every shot that was recorded by that receiver. As well, the S keyloc and R keyloc parameters in SUMatrix do not actually have to be shot keys or receiver keys at all. Below, CDP numbers are computed, for example, by SUBin CSV, and then CDP and offset keys are used in SUMatrix. Note, the S divider effectively bundles 4 CDPs together, while the R divider effectively creates 25-meter offset bins. Anytime multiple traces try to occupy the same position in the matrix, only one of them is retained. The result is this, which gives another perspective on the refraction model. But you might find it interesting to do this for a post-NMO reflection horizon. You have to pre-apply a time shift to align with your desired horizon. After SU Near Surface Zone CSV, you can use SU StackUp to create shot and receiver stacks. Once flattened, refraction wavelets can be stacked just like reflections. A receiver stack of refraction wavelets. Note the small time shifts at some receivers. Those shifts are, of course, the consistent small time shifts seen earlier when we were looking for geometry errors. The shot stack will have time shifts as well. These are similar to surface-consistent residual statics, but if you choose to apply these shifts to reflections, usually set SU shift CSV S mult and R mult parameters to about 0.75 scale factor because the refraction paths are angled near their ends, but reflection paths for statics are vertical. Also, after CDP numbers are computed by SUBin CSV or otherwise, you can run SURes CSV on the flattened refraction wavelets to try to determine the time shifts. You should zero out or delete samples greater than the wavelet time before doing this. Again, if you choose to apply shift values obtained this way to reflections, usually set SU shift CSV S mult and all mult to 0.75 scale factor because refraction paths are angled near the ends, but reflection paths for statics are vertical. Why try to use SU StackUp or SURes CSV on refraction wavelets? Because sometimes reflections are so noisy, weak, or dipping that deriving any residual statics from them is difficult. Using shifts derived from refraction wavelets might bring reflections into enough alignment that you can then use SURes CSV with the reflections. The documentation of SU Near Surface Zone CSV and SUMATRIX follows, so you can read it here conveniently. I remind you the documentation can change after this video, October 2024.